This is your first introduction to control systems, which is really cool that you get to see it at the sophomore level, at the very end of sophomore level. It's typically a junior level concept, so yes, we understand that, but we're also putting it to a sophomore level, so it's something that you can understand. And what's great about this lab is that you really get an understanding for what these gains mean, that truly if you're just doing a theory-based class in controls is a lot harder to understand and appreciate. So we're going to talk about that a little bit today. So what we have for you in the next couple weeks are these control arms. We have two different versions. There's a rigid arm and a flexible arm. And these are going to be modeling what you might see in a spacecraft application, where you're pointing part of the spacecraft towards, say, the sun. Like if you have an appendage that has solar panels on it, you might need to point that in the direction of the sun so that you can maximize your solar input onto those panels. So the first easiest approximation for doing a control arm is to control something that's completely rigid. So that's what we have here. And we're using this rigid arm to point it to angles that we desire. So we can control, right now I'm commanding it to do a step response and go plus or minus 0.3 radians. So it's going to 0.3 radians and then minus 0.3 radians, and then back and forth, just to show how it responds to that pointing maneuver. We'll start with that today. After this demo, you'll get to actually go to the different core units that we have and get some experience with the different gains that we have and how do those gains actually compare to the performance. If I increase those gains, I can increase the motor voltage. If I increase the voltage going to the motor, it's going to move faster. What happens if it moves too fast? Intuitively, what do you think happens if it moves too fast? How does it get to my target? Somebody said it. Overshoot. Exactly. So if I try to move too fast, I could overshoot my target. I could say I want to go to 0.3, but I'm going so fast that I can't stop by the time I get to 0.3 radians, so I go past and I overshoot, and then I have to come back, right? So we can adjust our gains and adjust the actual parameters of the system just by adjusting these values. What we can do is we can actually artificially add damping. So we can add the natural damping in the system, which there's some friction and some viscous effects that can add stiffness and damping. We can actually add to that by changing these gains in the equation. And we can actually add damping to the system. When we add damping to the system, now it's no longer going to overshoot. It might even be overdamped. So it might not ever actually get there. So here, I'm commanding it with this step response, which is in white. So I'm telling it to go to 0.3 radians and then minus 0.3 radians. The red line is my actual response. So it doesn't quite totally get there. There's a couple of reasons why that is. Part of it is that we're close to critically damped. So remember back to your calculus classes, right? You've looked at these systems, critically damped, underdamped, overdamped. You've seen this before, yes? Do I get a couple nods, yes or no? Okay, people have seen this before? This is your perfect application of that. You've seen that theoretically, you haven't really got to see that physically yet until this lab. And that's what I think is really cool about it. So if we're at this critically damped case, we should get right to our target. It should be our perfect case. But we actually have some physical effects that maybe don't let us get there. For example, even though we don't quite get to 0.3, we get to 0.25 radians, we still are commanding a voltage. So the control system is still doing its job. It's trying to compensate for that error. It's saying, give me a little bit of motor voltage to try to get that arm to go up to 0.3. But the reason why it can't reach it is that the motor voltage isn't enough to overcome the initial inertia. So you know if you command a motor voltage to start, or even if you're just driving your car, if you just give the car a little bit of gas, there's not enough for it to actually start moving until you overcome the inertia that you need to actually have it get going. And we call that the dead band. So that's the dead band area where we haven't given it enough voltage for it to actually overcome that initial starting. And then once it gets started going, then it'll move. So we have to overcome that friction. We don't have that available in this system because we are only going to do for this class, since it's sophomore level, we don't want to push things too much. We're not going to do too much in controls. We're not going to do a full PID controller. A PID controller would do proportional gains, integral gains, and derivative gains. So what do we mean by that? As you start getting into the equations and the theory in the class, this will make a lot more sense. So it's okay if I don't make sense yet. It will make sense more later. But just imagine that I could apply a gain to my system to apply voltage to the motor that is proportional to the error in its position. If I'm at 0 and I want to go to 0.3, that's an error of 0.3 radians. I can multiply that error by some gain called K1. That K1 proportional gain is listed here. It's a gain of 3 right now. So any error I have in where I am versus where I want to go is multiplied by a factor of 3. And that's going to say, okay, move really fast until that error is minimized. Once that error is minimized and I'm closer to my target, then that motor voltage is going to shut down. So this plot shows my motor voltage. Initially, my error is very large, so the motor voltage is going to spike. And then as it gets closer and closer to its target, it's going to ramp down. That's controlled by these gains. Okay, so that's proportional gain. So proportional gain is proportional to the error of my position. Simplest concept, just to start there. Now let's add in the next one, derivative gain. So we have our derivative gain, K3. Now we can add in an extra motor voltage. So we're going to say add in the voltage contribution from the proportional error, add in the error due to derivative. Now I'm going to add in and say, okay, what is the speed of what my system is doing? How fast is it moving? If it's moving really fast, then I want to change its position, change its velocity so that it gets down to 0. Because at the end I want to be able to stop. So if my velocity is very high and my error is very high, I'm going to get a large motion in my motor. Once I get to where I want to go and my position error is very low, I want to also slow down my velocity so I can also slow that down and reach my target. So think of the derivative gain as adding damping because it's proportional to the speed of the system, which if you look at your basic spring mass damper, something that's proportional to speed is a damping coefficient, right? So my damping coefficient that I'm artificially adding to the system is this K3 derivative gain. Notice that my proportional gains are much larger than my derivative gains. So as you start calculating your own gains based on the theoretical equations, if you start getting numbers that are very large, like on the order of 10 and 20 and 100, you probably have a math error somewhere, and you want to go double check your math. So typically we're going to have proportional gains in the single digit range, and we're going to have derivative gains less than 1, some kind of fraction of 1, okay? So there's a lot of information there that I just threw out at you. Hopefully some of it absorbed. It's going to absorb more as you get on through this lab. But what we're trying to do as engineers is we're trying to control the system so that it behaves exactly the way we want it to. Next thing I want to do is let's do a hold position. So I'm just going to tell it to hold at 0. So So I'm going to tell it to go to 0 degrees, and I'm just going to tell it to stay there. So let's say that I want it to point at the sun, and the sun right now is my lab station, and I want it to just stay there. What if it gets an external disturbance? So some kind of external thing hits my satellite. Let's say it hits a small little asteroid or a small little debris, and it tries to throw it off track. The control system can then regain that position and bring it back to where it's supposed to point. So if I give it a disturbance and I tell it to move away, and I bump it away from its direction, the control system will bring it back. So notice that it tries to maintain that 0 degree position. Again, we still have the deadband, so plus or minus about 0.05 radians of deadband of the motor, but we're going to call that close enough to 0 for our purposes, okay? Because we have to just be 0 plus or minus 0.05. That's good enough to be pointing at the sun. We're still going to get good sun coverage. So right now, let's try doing hub proportional of, let's bump that up to 5. And then let's turn the derivative gain off. So this is what I want you to do for the rest of the class when you come up in groups and start working with the hardware. I want you to get a physical feel for what these gains actually do. So I want each person to hold the position, command it to hold at 0, and then each person feel the difference as you try to disturb this arm and it fights you to bring it back. So right now, with just proportional gain, it will come back to its position. And the more I increase that gain, let's increase that up to like 7, it's going to fight me even harder. So you can't see that right now, but when you try it later today in lab, you can feel that difference of it, the motor actually fighting you more than how more you push it, it fights back. This proportional gain acts like a spring constant. So think of that. Your K1 proportional gains are like adding stiffness to the system. Okay? Now let's turn proportional gain to 0. Now let's just do derivative gain. So let's do derivative gain of 0.5, let's do 0.3 maybe to start out with. That's probably better. So notice with this that proportional gain is 0. Proportional gain is the gain on the error of the angle, and it's trying to hold its position at 0. So if I move it to a different position, it doesn't care. It can't fight its position. It can't bring it back to 0 degrees. Because there's nothing in the control law to control the error of the position. So it has multiple stable points. It can be stable at any point that is 0 velocity. Because the only thing that we're feedback controlling right now is derivative gain. So all it cares about is if the velocity is 0. So any point where the arm is stationary is a happy place. So I can put it anywhere that it's 0. The more I try to move it and the faster I try to move it, the more the motor fights me, and that derivative gain is counteracting how fast I try to move. So the more velocity error I have away from 0, the more voltage is applied to fight me. Okay? Now when you combine both of those is when you can control both velocity and position. Right now I'm just controlling velocity. Any questions about that? So you kind of start to see the difference between proportional and derivative gains and why we need both of them, not just one or the other. Now let's get kind of crazy and start thinking about what happens if our gains are negative. What is that going to do? Any idea? So physically it's hard to kind of think about. Again, don't have a physical construct for a negative spring or a negative damper. Those don't really exist in physics. But in controls, we can actually do that. So by putting in a negative K1 proportional, that's like a negative spring constant. By putting in a negative K3 derivative, that's like a negative damping. So let's see what happens. Let's do a negative, let me get that back to 0 so it's closer to some happy place. All right, let's try negative 1. So at this point, everything's fine. It's pointing at 0 degrees, so there's no error. There's no amplification to the motor. The motor voltage is 0. The gains are fine. But as soon as it goes away from 0, it's going to continually go away from its stable point. So it's an unstable system. Now let's bump that up even higher so you can see it more dramatically. Let's try negative 3. I'll bring that back to 0. So it's at 0, no error. No error in the system. As soon as I give it an error, instead of coming back to 0, it just goes unstable in the opposite direction. So that negative gain is just taking that error and amplifying it, feeding it back into the system and saying, go even faster in the wrong direction, and now go even faster in the wrong direction, until the point that it hits our physical stop. We programmed into the software 270 degrees so that it doesn't just spin itself into breaking itself apart. So for safety of the system, we put in a physical stop, but this instability would just go off to infinity and just start spinning as fast and as fast as it can go because of that negative gain. So that negative gain is unstable system. It's like balancing a ball on the top of a hill. It's happy as long as the arm is at 0 degrees, which is the top of the hill. If I bump it in either direction, it's going to fall off the hill and keep going as fast as it can go, and faster and faster and faster. Now let's try doing negative damping. So we'll set our proportional to 0. Our derivative is going to be negative. So we'll set that to, what do you think, Bobby? Negative 0.5 to start out with? Let's try negative 0.5. We'll see what happens there. So now with negative 0.5, this system is going to be happy and stable if it's at 0 velocity. So it shouldn't care if I move it to another position, right? Because it doesn't have any control over the angle error. So as long as I move it to another position, everything's happy. I don't think that's going to be strong enough. Let's do negative 1. Doesn't feel quite strong enough to me. But now if I give it any kind of velocity, it goes unstable. Because that velocity, which is no longer 0, gets multiplied by a negative derivative gain, that negative 1, and then that velocity just increases. That negative gain amplifies that negative velocity, and it goes completely unstable and would spin around incessantly if we didn't have the stops. But what's cool is I can actually put it to 0 velocity, and then it's happy at any position. So I have almost an infinite number of stable positions as long as the velocity is 0. What's fun about this one is you can actually use it to bounce off of your hands back and forth. Because as it keeps bouncing off one hand, it gets a velocity in the other direction. And so that negative gain just continues to amplify that velocity. But as long as I hold it stationary, it's stable. So it's kind of pseudo-stable as long as the velocity is 0. So that's what I really want you to get out of today, is to appreciate the differences of proportional and derivative gains and how positive and negative gains can affect the system in stability. And then as the weeks go on, you'll get to learn more about the actual equations and the math behind this, which is really, really cool. It's one of the best applications that we have, one of my favorites at least, where you get to actually see the critically damped, underdamped, overdamped cases. You'll get to predictively predict what gains you think you should use for K1 and K3 to perfectly track that square wave as best as you can given the dead band of the motor. You have a couple of limitations. Of course, since this is sophomore level, you're just going to be analyzing this with basic assumptions. You're going to be neglecting friction. We're not going to put that into the model. But there is friction here. The friction is very low. We have nice low friction bearings. So it's not going to be a large effect, but there will be some effect to that. So there'll be a little bit of discrepancy between your predicted gains from the model versus your actual results when you test it on the hardware. And this is very typical in control systems. What we do is we take our model, we make our assumptions, we get us close to what we need for our gains. Then we come in on the hardware and we test the hardware. And then we tweak our gains. So we adjust them a little bit. And that's where you need the understanding of, do I need more stiffness or do I need more damping? Do I need to get faster to my target because I'm not getting there fast enough in my response time? Because we give you response time. You need to get from point A to point B in X number of seconds. If I'm not getting there fast enough, I need to increase my proportional. If I'm overshooting my target, I need to increase my damping because I'm overshooting. And we can use those as trade-offs to tweak our K1, K3 gains. So you're going to use the math to get you close, and then you're going to come in with your understanding of stiffness and damping to tweak those gains to get them even closer experimentally. And then you'll take those experimental gains that you determine and say, yeah, those look really good. Take that, save that data, feed those gains back into your model that you have, and then compare your tweaked experimental gains with your model of what those gains should do, and see how those match and overlay those plots. Predicted response versus actual response. And that's the objective of the lab over the next several weeks. Okay? All right, so in terms of the operation of the VI, how do we actually take this data? So let's look at that. We have the run button in the top left, typical of all your lab UVIs. Don't use the stop button. That aborts the VI. That's especially important in this case, because if you abort the VI in the middle of its operation, it's just going to continue to do its control system, which may or may not be unstable. And you don't want to leave it in that state. So you always want to use the emergency stop button and the stop VI button when you're done taking data. We also have put in, Bobby's put in a really nice feature. You can just use the escape key. So go ahead and hit the escape key. Stop is activated. That'll stop the control. Everything's happy. And then escape button again will toggle you back into run mode. That's especially important today. You're going to be able to work on the hardware today, and I'm going to give you a spreadsheet. Let's pull up that spreadsheet. This spreadsheet gives you a range of values that you can use. This top section right here for the rigid arm. So I'm going to let you use unstable gains. I'm going to let you use negative gains from -2 to 5 and -0.5 to 1.5. But I'm going to do that with the caveat that you're responsible for stopping the system if it goes unstable, because I don't want you to break our hardware, okay? Because it can strip out the gears, it can mess up the shaft collar and all of the attachments, and then we have to go rebuild it. And we want these to last for the next several weeks and actually the next several years. So it's your job as the user to go ahead and find these unstable cases, but quickly be ready to hit that escape button when you do see the unstable case, okay? So that's why we have that escape button. Next thing you need to do after you run the hardware, select which unit you're using. We have 8 different units, if you can select on that, Bobby. We have 4 different rigid arm units and 4 different flexible arm units. I'll talk a little bit more about the flexible arm in a minute. But you need to, for today, you're just going to be using the rigid units. Because I don't want you to play around with unstable gains on the flexible arm. It's too fragile. So it's not going to be robust enough to handle that. So for today, until you actually have predicted gains, you won't get to use the flexible. You'll just use the rigid arm. Make sure you select the right unit. That puts in the right factors for conversion to make sure that we get the right conversions for displaying our sensor values. So let's talk about that. How are we measuring angle? So the only thing we need to measure is the angle of this arm. The angle of this arm is measured by a potentiometer, which is this yellow cylinder at the base. That potentiometer is calibrated to measure the angle position of the arm. That's the only sensor feedback we have. Then we take that and plot that on the hub angle plot here on top. So that's our actual hub angle from the potentiometer. Then the LabVIEW program takes the derivative of that to calculate the hub angle velocity. So that's just the derivative of the potentiometer position. Tip deflection and tip velocity apply to the flexible arm. So for today, you'll be ignoring those. Then the only control output we have to the system is a voltage that goes to the DC motor. So there's a DC motor right here, offset by a gear, and you'll be looking at the gear ratios when you go into your equations in the coming weeks. But this offset motor is what's driving this arm to change its position. So that control voltage that's being sent to that DC motor tells it how fast to move. That's being displayed on the bottom right plot in volts. You do have a physical limitation in the system. You cannot command out from the DAC system more than 5 volts. That's all it can handle. So if you try to apply too much gain and your theoretical gains say, well, if I really want to get there fast, I want to have gains of 10 and 0.5, the system may not physically be able to do that. And you will see it cut off. Let's actually show that. Let's do like a gain of 10 and a damping ratio of 0.1 and just try to get it to do a step command. Kind of cut it off, but not for very long. Let's try to add, let's bump that up even more to about 12. So it's more pronounced. So if you look very closely right here, the control voltage gets up to 5 volts, and then it gets cut off. So it gets what I call flatlined. So that's the physical limitation. The voltage can't, even though the gains are trying to get it to go above 5, the system is cut off at 5. So you're not reaching that. That is a condition that you want to avoid. So if you notice that in testing, and you're getting past the limits of control voltage of 5 volts, your linear equations that you have don't apply anymore. So you can't compare your physical data with your experimental data because you're not modeling the limitation of the control voltage. So if you run into that case, which is very possible, very likely, you have 2 options. You can reduce your step amplitude, because in the objectives we tell you to move a step command, but we don't tell you how much you have to move. So in order to stay within the limitations of the motor, you can reduce the amplitude. Then the motor doesn't have to work as hard. Or you can adjust your gains and bring your gains down, especially your proportional gain, which is telling it to go too fast. You can reduce that down, and now you can get back to that 0.3 radians without exceeding 5 volts. So those are your design constraints. This is a design problem for an engineer, very typical in aerospace systems. To design a system, to do performance based on your limitations and how much friction and what the motor voltage can do. Okay? The lab assistants are always really excited about this lab. This is one of their favorites. Bobby and I also are very passionate about this lab, Chris, and also the TAs who've run through it with us yesterday. So I know that was a lot of information. That's okay. You'll have a lot of questions as we go through this. Please ask them. We're happy to talk to you about it. Another thing I want to mention to you is the control system is not being run in LabVIEW. The control system is being run on the MyRio, which is local to the spacecraft. So imagine the computer and the LabVIEW interface is just your ground station. Your ground station is sending position commands and then reading back the performance position of what actually occurred. But it's not doing any of the implementation of the control gains, and all of that math is not happening on the ground station. It's happening on the spacecraft. So if I unplug the LabVIEW computer and just unplug its data line, it's just going to keep doing its control system, because that's what I last told it to do. I can no longer update. I've lost communication with my satellite. My ground station is now disconnected from my satellite, and it just keeps doing its thing. So I mention this because it's important. If it goes unstable and you leave an unstable controller loaded onto the spacecraft, it will continue to be unstable until you give it a new command. Okay, so that's an important thing that I want to point out of where the control is actually happening. Alright, now we'll plug our ground station back in so we can send new commands. Another reason why it's important to shut it down properly. Just closing out the LabVIEW program and Xing it out might leave the controller on there. It's just going to keep running until you power cycle, because we programmed in for it to restart from 0 once we power cycle the unit. Okay, so a couple of things I want to mention here. This switch, the enter values for the gain constants, this is a toggle switch. If you toggle that, you can use the default values, which are built in, or if you toggle that over to enter values, now you're allowed to control and enter your own values. So that's what that switch does. You can also control the step amplitude, how far in degrees, actually in this case we do radians, how many radians do you want it to move, and then you can also control the step duration. How long does it stay at that position? So does it stay at that position for 10 seconds, 5 seconds? You want to give it some time to stable out. So in case it oscillates, especially with the flexible arm, it might need some time to damp out before you switch to the next position. So you can adjust those values as needed for the step duration based on just your observations. Then once you get gains that you're happy with, that you want to take some data on so you can analyze, you want to hit the Save Data button. So that Save Data button, you want to select that. That's going to ask you where you want to save your data. So we have folders in there for each of the 3 sections for you to save your data in. And you will not be saving this data to share as a class. It's just for you and your group. So you can call it whatever you want. There's no naming convention because we don't need to share data. And then say OK, and it'll save that. And this is your desired data size. So your desired data size needs to match up with your step duration. If I have this set to 1 second and my step duration is 5, I'm not even going to get an entire step of data. That would be useless. So you want to make sure that your data size is probably at least 2 or 3 times larger than your step duration, so you can get a couple cycles in the data file. Okay? So the data that is saved is not save data and then save future data. It'll save the previous 10 seconds in this case. So when it looks good on the screen, then you hit save data, it'll save the previous 10 seconds that you saw on the screen. So that's an important point. It's important to get a couple of cycles. It's also important to keep track of which unit you're using, because each of the units acts a little bit different. They have preferred direction. Some of them track better on the left side versus the right side, or vice versa. And you can use whichever side matches better. So if it tracks better going to the right, like in this case, it's tracking a little bit better going this direction, I would choose to extract this data set and ignore the data set going in the other direction. Okay, let's see, what else? Let's talk about the flexible arm really quick. After you've gotten real comfortable with the rigid arm in the next week or so, then we're going to also start moving to the flexible arm. And this is where the dynamics in the equations get a lot more interesting. So doing the rigid arm is really kind of pretty basic. Doing the flexible arm now is really more representative of what you'd see in a real spacecraft. Most of the time our solar panels are not going to be rigid. They're going to be flexible. And if we move them too quickly, we could bend them so much that the solar panels are actually going to crack and break. So this is where the control gains and the performance are really important. We want to be able to point it towards the sun, but not have it overshoot or oscillate too much to break the solar panels. So this is where your equations are going to get really interesting. Now we have two sensor feedbacks. We still have the same potentiometer for angle of the hub. That's our hub angle. So that's our pointing position. But we also now have a sensor to tell us how much is the tip deflecting. Because I do not want this tip to bend too much or my solar panel is going to break. So the tip deflection is read out here in meters. So that's how many meters this tip has deflected in this perpendicular direction. We measure that with strain gauges. The strain gauges are placed at the base, which is where the point of maximum strain occurs in a bending beam equation. So if you think back to your bending beam equations, the more I bend this, the more strain I get right at the clamped point. So that's why the strain gauges are placed here. They are extremely fragile and extremely expensive, so be very careful with them. And also the wires coming from them, that they don't get broken. We have some physical stops here, so that if it gets too unstable, it can come around and hit those stops and not rip off the wires. But we still need to be careful with it, which is why we're not going to play with unstable gains on this unit. Let's go ahead and look at, actually I don't want to hook it up because it'll take too much time. But this one is using the strain gauges fed back through a conditioning board and then sent to the same MyRio. So it's just an add-on to the rigid arm with additional features. This extra sensor gives us 2 more gains that we can play with. So if you can select Unit 4 Flexible just to show how those gains show up. Now we have PD control of our hub angle and PD control of our tip. So we have our proportional gains and our derivative gains for each. They're labeled here, K1 through K4. Then we also have these plots, which have our tip deflection and our tip velocity. So tip deflection is measured from the strain gauges, and then that deflection, called little d in your equation, is also taken the derivative of to get d dot, which is your tip velocity. And now we can apply gains K2 and K4 to control how the tip is operating as well. So if the tip is deflecting too much from 0, that K2 proportional gain will bring it back to 0. If the tip is moving too fast, that velocity will be reduced by the tip derivative K4. So now we can actually make this flexible arm operate like a rigid arm. And we'll have you play around with what if you just put gains in here and don't have K2, K4? How does it work? You'll see how much it oscillates because we don't have that feedback on the tip. And then once you implement K2 and K4, you can see how you can reduce that tip deflection down to almost zero. Also, the strain gauges are extremely sensitive. They're so sensitive that they can actually see the little air currents of the tip as it's moving. So you'll see that this tip deflection never gets perfectly to zero. It's going to oscillate very slightly around zero. And again, we don't have enough motor voltage. You want to? Okay. You don't have enough motor voltage to overcome that slight variation in the tip deflection. So you'll notice in the lab document that we tell you to get the tip deflection down to some plus or minus. You don't have to get it perfectly to zero, because that's not possible. But we want you to get it to within our error bounds of zero. Now you have what's called a single output, multiple input system, MISO. So what we have for feedback is two sensors, our strain gauge and our potentiometer, but we still only have the single output, which is our DC motor. All of these gains together, K1 through K4, all add up against their errors. So K1 times the error of position, K2 times the error in tip deflection, K3 derivative, K4 derivative. All of those add up to one motor voltage that's sent to the DC motor. So that control voltage will still be applied to and shown to you, and you have to make sure that that doesn't exceed 5 volts. So now let's use the one thing I want to point out that kind of trips people up the first time is, remember before when I said negative gains were unstable? There's one exception to that, the K2 gain. K2 gain actually has to be negative in order to be stable. It's reversed of all the other gains. And the reason is if you move the hub in one direction, the tip is going to go in the opposite direction. Just the way the dynamics work. If I move the root here, the tip's going to go this way. If I move the hub this way, the tip's going to go the opposite direction. So there's an inverse relationship between the hub angle and the tip deflection. So when we go to put gains in, and as you're calculating gains, K1 will be positive, K2 will be negative, K3 and K4 will be positive. Because the velocity we still want to have proportional to positive velocities. And derivative K3 is always positive, as it was before. The only one that needs to be negative is K2. If you put in positive gains for K2, that's now unstable. So it's the inverse relationship. And that's just due to the dynamics of the system. Now that we have this plugged in, you can see that the strain gauges are very accurate and really sensitive. So they've tried to actually measure all of these little deflections. Even right now, looking at it, you can barely see this moving just because of the air currents. And each of the units is going to be a little bit different. So again, it's important to know which unit you're doing. Let's just do a quick test to wrap it up. Let's do a step position of 0.3. So when the strain gauges start up, they're going to have a little power applied to them, and that's going to cause an offset. That offset needs to be taken out in the software. So you can see this isn't oscillating quite around zero. It's close, but it's a little bit off. We can fix that offset by hitting the escape or the emergency stop. That'll reset the hardware, so it'll re-zero, and then start it again by toggling back. And now we'll be oscillating a little bit better around zero. Now we can show, let's actually do like 5. Let's do a step response of just 0.3, and we'll just do proportional. So you can see how bad it oscillates. Without any feedback control, you can see that this system is clearly not critically damped. It goes to where it's trying to go, and then it oscillates and then eventually damps out. So this is the natural damping ratio of the system. That's how long it takes for it to damp out with without any control system added. But you're going to improve upon that by adding in these tip derivative gains so you can damp out that tip deflection so it doesn't oscillate so much and it just gets right to where it's supposed to go. And you can see that here as well, that the base is oscillating and not reaching and tracking that square wave. You can improve upon that with your control gains that you're going to design.
One other limitation we have here has to do with the derivative and how that's being calculated. So we're taking the derivative just from the position sensor. So you can see once this chart zooms in a little bit that there's some noise on that. So when you take the derivative of the noisy signal, that noise basically becomes amplified or carried over onto the derivative portion as well. So then when you apply a gain to that, then your velocity contribution could become noisy, and then that is another contributor for the physical limitations here. So you can see how noisy this hub velocity is, even when we're not moving. So you apply a gain to that, and that noise just then gets fed back into the motor controller.
So that's why large derivative gains are not feasible because of the noise.